class in calculus. For today, we will take up integration of hyperbolic functions. But first, we do a quick review of the definitions of hyperbolic functions, the basic identities involving hyperbolic functions, and the formulas for differentiation and integration of hyperbolic functions. We start with the hyperbolic sign. It is defined as the difference of e to the x and e to the minus x over 2. Hyperbolic sign is defined as e to the x minus e to the minus x over 2. And hyperbolic cosine is defined as the sum of the exponential functions e to the x and e to the minus x all over 2. The hyperbolic tangent, as with the tangent of an angle in plane trigonometry, is defined as the ratio of the hyperbolic sine of x and the hyperbolic cosine of x. And we have shown last time when we substitute the value of hyperbolic sine of x and the value of hyperbolic cosine of x, and we simplify the expression, we would get hyperbolic tangent of x equals e to the x minus e to the minus x all over e to the x plus e to the minus x. And the last three hyperbolic functions are the reciprocals of the first three hyperbolic functions. The reciprocal of the hyperbolic sine is called the hyperbolic cosecant of x. And the value of the hyperbolic cosecant of x is the reciprocal of this ratio. And the reciprocal of this is 2 over e to the x minus e to the minus x. And the reciprocal of the hyperbolic cosine is known as the hyperbolic secant of x, and its value is equal to the reciprocal of this expression, which is equal to 2 over e to the x plus e to the minus x. And the sixth and the last hyperbolic function is the reciprocal of the hyperbolic tangent of x. And it's equal to the reciprocal of this expression, which is equal to hyperbolic cosine of x over hyperbolic sine of x. Or the hyperbolic cotangent of x is equal to the reciprocal of this expression, which is equal to e to the x plus e to the minus x all over e to the x minus e to the minus x. And there we have the 6 hyperbolic functions. Now we write the basics of the basic identities involving hyperbolic functions. The first is the difference of the square of hyperbolic cosine and the square of hyperbolic sine is equal to 1. And the difference between 1 and the square of hyperbolic tangent of x is equal to the square of the hyperbolic secant of x. And the next identity says that the square of the hyperbolic cosine of x minus 1 is equal to the square of the hyperbolic cosecant of x. The hyperbolic sine of twice an angle, where x is the angle, is equal to 2 times the hyperbolic sine of x multiplied by the hyperbolic cosine of x. And the hyperbolic cosine of twice an angle, or hyperbolic cosine of 2x, is equal to the sum of the square of the hyperbolic cosine of x and the square of the hyperbolic sine of x. Now we write the first formula for integration of hyperbolic function, in particular the integral of hyperbolic cosine of x with respect to x is equal to the hyperbolic sine of x plus a constant of integration c. And this is the first of the formulas for integrals of hyperbolic functions. The integral of hyperbolic cosine of x with respect to x is equal to hyperbolic sine of x plus c. For our first example, consider the following integral. We are given the integral of hyperbolic cosine of x with respect to x over 2 plus 3 times hyperbolic sine of x. To evaluate this indefinite integral, we make use of substitution. We know that the derivative of hyperbolic sine of x is hyperbolic cosine of x. If we know that the derivative of hyperbolic sine of x with respect to x is equal to hyperbolic cosine of x, we may let u be equal to 2 plus 3 hyperbolic sine of x, because the derivative of hyperbolic sine of x is hyperbolic cosine of x, and we have hyperbolic cosine of x in the numerator. Thus, we let u equals 2 plus 3 times hyperbolic sine of x. And we differentiate both sides. Derivative of u with respect to u is 1 times du, or du. And derivative of a constant is 0. And the derivative of 3 times hyperbolic sine of x is equal to 3 times derivative of hyperbolic sine of x, which is equal to hyperbolic cosine of x. Thus, derivative of 2 plus 3 hyperbolic sine of x equals 0 plus 3 times hyperbolic cosine of x, which simplifies to 3 times hyperbolic cosine of x. And we multiply by dx. But we have hyperbolic cosine of x dx in the numerator. So we solve for hyperbolic cosine of x dx from this equation by dividing both sides by 3. If you divide the right hand side by 3, 3 hyperbolic cosine of x dx divide by 3, you get hyperbolic cosine of x dx. And we also divide the left hand side of this equation by 3, du divide by 3. Now, the given integral is now equal to the integral hyperbolic cosine of x times dx is equal to du over 3. Du over 3 because we divide both sides of this equation by 3. The right hand side divide by 3, you get hyperbolic cosine of x dx is equal to du divide by 3. So this is equal to the integral of du over 3 over 2 plus 3 hyperbolic sine of x is what we let as u. And we simplify this expression, the integrand. Because 1/3 is a constant, we take it out of the integral sign. And we get the integral of du over u, and it's equal to ln of u. Plus a constant of integration. And in the final answer, we now replace u with 2 plus 3 times hyperbolic sine of x. Hence, the integral of hyperbolic cosine of x dx over 2 plus 3 times hyperbolic sine of x equals 1/3 times ln of 2 plus 3 times hyperbolic sine of x plus a constant of integration c. We take another example. For our second example, consider the following integral. We want to evaluate the integral of the square of hyperbolic sine of x with respect to x. For this example, we make use of two identities, the difference of the square of hyperbolic cosine of x and the square of hyperbolic sine of x, which is equal to 1. And the identity for the hyperbolic cosine of twice an angle, which is equal to the sum of the square of hyperbolic cosine of x and the square of hyperbolic sine of x. These are the two identities that we will use to simplify the given integral. We start with the hyperbolic cosine of twice an angle equals hyperbolic cosine squared of x plus the square of hyperbolic sine of x. In this equation, we replace hyperbolic cosine squared of x with an equivalent expression from this equation. From this equation, we solve for the square of hyperbolic cosine of x by transposing the square of hyperbolic sine of x to the right-hand side. Hence, from the first identity, the square of hyperbolic cosine of x is equal to 1 plus the square of hyperbolic sine of x. This is now positive because we transpose negative hyperbolic sine squared of x to the right hand side. And in this equation, we replace the square of hyperbolic cosine of x with 1 plus the square of hyperbolic sine of x. The hyperbolic cosine now of twice an angle, or 2x, is equal to the square of hyperbolic cosine of x is equal to 1 plus the square of hyperbolic sine of x plus the square of hyperbolic sine of x. From the right hand side, we combine like terms. The last two terms are like terms, and their numerical coefficients are each 1. So this is 1 hyperbolic sine squared of x plus 1 hyperbolic sine squared of x equals 2 times the square of hyperbolic sine of x plus 1. And from this last equation, we solve for the square of hyperbolic sine of x, and we will replace the value of the square of hyperbolic sine of x in the given integral. We transpose 1 to the left hand side, and at the right hand side, we are left with 2 times the square of hyperbolic sine of x. And we transpose 1, this 2 times the square of hyperbolic sine of x is equal to hyperbolic cosine of 2x, transpose 1 to the left, minus 1. And to get the value of the square of hyperbolic sine of 2x, we divide both sides of this equation by 2. Or we multiply the left hand side and the right hand side by 1/2. We multiply both sides by 1/2, or we divide both sides by 2. Multiplying the left hand side by 1/2, we get the square of hyperbolic sine of x. And we do the same with the right hand side. We multiply the right hand side by 1/2. And the given integral is now equal to we now replace the square of hyperbolic sine of x with 1/2 times quantity hyperbolic cosine of 2x minus 1. And we integrate with respect to x. So this is now equal to the integral of 1/2 but 1/2 is a constant, so we can take it out of the integral sign. So this is now equal to 1/2 times the integral and we apply one of the properties of integrals. The integral of a sum or difference is equal to the sum or difference of the integrals. The integral of hyperbolic cosine of 2x minus 1 with respect to x is equal to the integral of the first term, hyperbolic cosine of 2x with respect to x, minus the integral of 1 times dx, or integral of dx. To integrate the first term, we let u be equal to 2x. To integrate the first term, we let u equals to x, and we differentiate both sides. The left-hand side with respect to u, derivative of u with respect to u is 1, multiplied by du is du. And the right-hand side we differentiate with respect to x, derivative of 2x with respect to x is 2, multiplied by dx. Hence du equals 2 dx. In the given integral, we have dx. Hence, we solve for dx from this equation by dividing both sides by 2. 2 dx divided by 2 is dx equals du divided by 2, du over 2. Hence, the given integral is now equal to 1/2 times the integral of hyperbolic cosine of u. We now replace 2x with u. Multiply by dx, and dx is du over 2. Minus the integral of dx. Again, 1/2 here is a constant, so we can take it out of the integral sign. And outside we also have 1/2. We take 1/2 out of the integral sign. The right hand side is now equal to 1/2 times 1/2 times the integral of hyperbolic cosine of u with respect to u minus the integral of dx. And this is one of the formulas for the integrals of hyperbolic functions. The integral of the hyperbolic cosine of x with respect to x is equal to hyperbolic sine of x plus c, and we apply this formula to evaluate the integral of hyperbolic cosine of u with respect to u, and it is equal to hyperbolic sine of u, and the integral of dx with respect to x is x, and we add a constant of integration c. We now complete the solution for the integral of the square of hyperbolic sine of x. The integral of the square of hyperbolic sine of x with respect to x is now equal to 1 multiplied by 1/2 multiplied by 1/2 is 1/4. Multiply by the integral of hyperbolic cosine of u with respect to u. We apply this formula for the integral of hyperbolic cosine of x with respect to x is equal to hyperbolic sine of x. So the integral of hyperbolic cosine of u with respect to u is hyperbolic sine of u. And 1/2 multiplied by negative is negative 1/2. And the integral of dx is x. Since we have integrated the two terms, we now add the constant of integration. And we replace u with its value. Earlier, we let u equals 2x. So this becomes 1/4 times hyperbolic sine of 2x minus 1/2 x plus c. The value of u is 2x. The substitution we used earlier. We now take another example for the integral of the cube of hyperbolic sine of x. To evaluate this integral of the cube of hyperbolic sine of x with respect to x, we make use of the identity for the difference of the square of hyperbolic cosine of x and the square of hyperbolic sine of x, which is equal to 1. And to make use of this particular identity, we write the cube of hyperbolic sine of x as the product of the square of hyperbolic sine of x and hyperbolic sine of x. So the cube of hyperbolic sine of x is equal to the square of hyperbolic sine of x multiplied by hyperbolic sine of x. And you can easily check this by using property of exponents. The base is hyperbolic sine of x and the exponents are 1, 2 here and 1 here. 2 plus 1 is 3. And to make use of this identity, we solve for the square of hyperbolic sine of x from this equation. We transpose negative sine, hyperbolic sine square of x to the right hand side and it becomes positive, the square of hyperbolic sine of x. This positive square of hyperbolic sine of x is obtained by transposing negative square of hyperbolic sine of x to the right. At the left hand side, we have hyperbolic cosine, the square of hyperbolic cosine of x. And we transpose positive 1 to the left hand side, we get minus 1. And the integral of the cube of hyperbolic sine of x with respect to x is equal to the integral of the square of hyperbolic sine of x, which we now replace with the square of hyperbolic cosine of x minus 1. The square of hyperbolic cosine of x minus 1 is equal to the square of hyperbolic sine of x. And we multiply this by hyperbolic sine of x. We integrate with respect to x. Again, we apply property, one of the properties of integrals. The integral of a sum or difference is equal to the sum or difference of the integrals. And this is now equal to the integral of the square of hyperbolic cosine of x multiplied by hyperbolic sine of x with respect to x minus the integral of hyperbolic sine of x dx. It's like you multiply each of these terms by the integral sign and hyperbolic sine of x dx. For the integral of the first term, we make use of a substitution. We let hyperbolic cosine of x be equal to u. And the second term is readily integrable. The integral of hyperbolic sine of x is hyperbolic cosine of x. This is one of the formulas for the integrals of hyperbolic functions. The integral of hyperbolic sine of x with respect to x is equal to hyperbolic cosine of x plus a constant of integration c. Earlier we had the integral of hyperbolic cosine of x is equal to hyperbolic sine of x plus a constant of integration c. First we rewrite this hyperbolic cosine squared of x as quantity hyperbolic cosine of x squared. The integral of hyperbolic sine of x with respect to x is hyperbolic cosine of x. And we first integrate the first term before we write the constant of integration. We write the constant of integration after we have integrated all the terms. For the first term, for this integral, we let u equals hyperbolic cosine of x. Because the derivative of the hyperbolic cosine of x is hyperbolic sine of x. Again, we let u equals hyperbolic cosine of x, and we differentiate both sides. The left-hand side with respect to u, derivative of u with respect to u is 1, multiplied by du is du. And derivative of hyperbolic cosine of x with respect to x is hyperbolic sine of x, multiplied by dx. In this integral, we replace hyperbolic sine of x times dx with du. And hyperbolic cosine of x, we replace with u raised to the power 2. The integral now of the cube of hyperbolic sine of x with respect to x is equal to integral of replace hyperbolic cosine of x with u is square. And we replace hyperbolic sine of x dx with du. Minus the integral of the second term minus hyperbolic cosine of x. And we simply apply the power rule to get the integral of u squared with respect to u. We add 1 to 2 and we divide by the sum, 3. Hence, the integral of u squared is u cubed divided by 3. Minus hyperbolic cosine of x, and we now write plus c, or constant of integration. And we write the final answer in terms of the variable x by replacing u with hyperbolic cosine of x. We replace u with hyperbolic cosine of x to the power 3 over 3 minus the second term hyperbolic cosine of x plus a constant of integration. But the cube of hyperbolic cosine of x is equal to hyperbolic cosine cube of x divided by 3 minus hyperbolic cosine of x plus c. Thus, the integral of the cube of hyperbolic sine of x with respect to x is equal to hyperbolic cosine cube of x divided by 3 minus hyperbolic cosine of x plus a constant of integration c. For our next example, consider the following integral. We want to evaluate the integral of x times hyperbolic sine of x with respect to x. For this integral, we apply integration by parts. And you recall that in the integration by parts, the integral of u dv is equal to uv minus the integral of v du. To apply integration by parts, we write the given integral in this form. And we let u equals x and this implies dv is equal to hyperbolic sine of x dx. For u equals x, we differentiate both sides. Derivative of u with respect to u is 1. Multiply by du is du. And we differentiate x with respect to x. Its derivative is 1 multiplied by dx equals dx. From this equation, dv equals hyperbolic sine of x dv equals hyperbolic sine of x dx. We get the value of b by integrating both sides. The left hand side, we integrate with respect to v. The integral of dv is v. And the right hand side, we integrate hyperbolic sine of x with respect to x. And the integral of hyperbolic sine of x is hyperbolic cosine of x. This is quite easy to remember. The integral of the hyperbolic sine of x with respect to x is hyperbolic cosine of x plus c. And the integral of hyperbolic cosine of x with respect to x is equal to hyperbolic sine of x plus c. Now we write the integral of x times hyperbolic sine of x with respect to x in this form uv minus the integral of v du. Using integration by parts, this is now equal to uv, u multiplied by v, or x multiplied by hyperbolic cosine of x. Minus the integral of b du. B is hyperbolic cosine of x multiplied by du is dx. So we get minus the integral of hyperbolic cosine of x with respect to x. The first term as is x times hyperbolic cosine of x. And the integral of hyperbolic cosine of x is hyperbolic sine of x. Since we have integrated the last term, we now write the constant of integration c. Therefore, the integral of x multiplied by hyperbolic sine of x with respect to x is equal to x times hyperbolic cosine of x minus hyperbolic sine of x plus a constant of integration c. For our next example, we evaluate the indefinite integral e to the x multiplied by hyperbolic sine of x dx. To evaluate this indefinite integral, we make use of the definition of hyperbolic sine of x, which is defined as e to the x minus e to the minus x all over 2. In the given integral, we replace hyperbolic sine of x with e to the x minus e to the minus x all over 2. So the given integral is now equal to the integral of e to the x multiplied by the value of hyperbolic sine of x, which is equal to e to the x minus e to the minus x all over 2. And we integrate with respect to x. We simplify. 1/2 here is a constant, so we can take it out of the integral sign. And we distribute e to the x multiplied by e to the x is e to the 2x. When you multiply e to the x by e to the x, you apply property of exponent. If the base is common, e to the x, you add the exponent, so x plus x is 2x. Now we multiply e to the x by e to the minus x. The common base is e, and we add the exponents, x plus minus x is 0. So that's minus e to the power 0 is minus 1. And we now apply one of the properties of integrals. We actually distribute the integral sign to each of these terms, and we distribute dx. So this is now equal to 1/2 times the integral of e to the 2x with respect to x minus the integral of dx. The second term is readily integrable. The integral of dx is x. For the first term, we make use of substitution. We let u equals 2x. Again, to integrate the first term, we let u equals 2x, and we differentiate both sides. Derivative of the left-hand side u with respect to u is 1, multiplied by du is du, equals derivative of 2x with respect to x is 2, multiplied by dx, we get 2 dx. In this integral, we have dx, so we solve for dx from this equation by dividing both sides by 2. 2 dx divided by 2 is dx equals du divided by 2. We have du over 2. And this expression is now equal to 1/2 times the integral of e to the 2x, but we let 2x be equal to u. We now replace 2x with u. And we also replace dx in terms of u. Dx is du over 2. Minus the integral of dx. Again, 1/2 here is a constant, and you can bring it out of the integral sign. We have 1/2 multiplied by 1/2 times the integral of e to the u minus d times the integral of e to the u with respect to u, or integral of e to the u du. Now we are ready to integrate each term, and we can also distribute now 1/2. The first 1/2 multiplied by 1/2 is 1/4 times the integral of e to the u with respect to u is e to the u minus the integral of dx is x. And since we have integrated both terms, we now add the constant of integration c. And we write u in terms of x. We let u equals 2x. Hence, the integral of e to the x multiplied by hyperbolic sine of x with respect to x is 1/4 times e to the 2x minus x plus c. For your practice, please try to evaluate the following indefinite integrals. Number 1, evaluate the integral of hyperbolic sine of x dx over 1 plus hyperbolic cosine of x. This is similar to our first example where we made use of a substitution. In this exercise number 1, you also make use of a substitution. You let u be equal to 1 plus hyperbolic cosine of x. Number 2, evaluate the integral of the square of hyperbolic cosine of x dx. In our example, we evaluated the integral of the integral of the square of hyperbolic cosine of x with respect to x. And for your exercise, you evaluate the integral of the square of hyperbolic cosine of x with respect to x, as with our second example where we made use of 2 identities. You also make use of the same 2 identities for number 2. Those are the square of hyperbolic cosine of x minus the square of hyperbolic sine of x is equal to 1. And the hyperbolic cosine of 2x is equal to the square of hyperbolic cosine of x plus the square of hyperbolic sine of x. Number 3, similar to our last example where we evaluated the integral into the x multiplied by hyperbolic sine of x. But in exercise number 3, you now have the integral of e to the 2x multiplied by hyperbolic cosine of x. For this exercise, you replace hyperbolic cosine of x with its value, which is equal to e to the x plus e to the minus x over 2. And multiply that by e to the 2x and simplify using properties of exponents, and you will get an integral of an expression in exponential function. And lastly, number 4, e to the x, evaluate the integral e to the minus x multiplied by hyperbolic sine of 2x. In the definition of hyperbolic function, in the definition of hyperbolic sine of x, we only have x, but here we have hyperbolic sine of 2x, which you can readily get or obtain from the hyperbolic sine of x. If we define the hyperbolic sine of u equals e to the u minus e to the minus u all over 2, and you let u be equal to 2x, you let u be equal to 2x in both sides of this equation, you will get hyperbolic sine of 2x is equal to e to the 2x minus e to the minus 2x. All over 2. So you make use of this value of hyperbolic sine of 2x equals e to the 2x minus e to the minus 2x all over 2, and multiply that by e to the minus x and simplify using properties of exponent. And after simplifying, you will get an expression in terms of exponential function that is readily integrable. And we will have more examples of integration of hyperbolic functions in the next lesson. If you have questions about the lesson today, please ask your questions in the comments below. Thank you for joining me in my class today in Calculus.